Question 2b and c. In an alternative arrangement, the gas leaving the dryer would be compressed to 10 atm and the temperature would simultaneously be increased so that the relative saturation remains at 50%. The gas then would be cooled at constant pressure to produce a stream containing 5 mol% of hexane. Calculate the final gas temperature, which is the temperature of the gas leaving the condenser, and the ratio of volumetric flow rates of the gas streams leaving and entering the condenser. State any assumptions you make. C. What would you need to know to determine which of the process, A or B, is more cost effective? Now for part B, we assume that no condensation occurs during the compression, meaning to say during compression the only changes made is the temperature and the pressure, in which it would be increased from 1 atm to 10 atm. So now look at this. Previously we had our gas stream leaving the dryer straight away to the condenser. Now we feed the gas into a compressor first, only then we feed it to the condenser. So the number of moles of the gas stream entering the compressor would be 2.18, with a mole fraction of hexane being 0.703 and nitrogen being 0.297 at 80 degrees Celsius and 1 atm. So we know from part A here we have found NO, which is the amount of gas that enters the condenser, would be the amount of gas that is the stream of gas coming from the dryer. Now, after the compression, the pressure increases to 10 atm as mentioned, and the temperature should increase so that the relative saturation remains at 50%. The gas leaving the condenser here would be 0.682 kilomole per minute, which is what we found also in previous question. There's no change because this is what we want it to be fixed. And the condition at the condenser gas outlet over here is 10 atm at a different temperature, Ti. So Ti is what we need to find, and the ratio of the volumetric flow rates of the gas stream leaving and entering the condenser. So we need to find V1 over VO, which is the gas stream that enters the condenser. So same thing, we use this equation here, to find our vapor pressure of hexane at that specific temperature. Now, we are told that in this stream here, the relative saturation is remain at 50%. So we have to take 0.5 to multiply over here. Multiply 0.5 over here. And that equals to the mole fraction of hexane multiplied by the total pressure in this stream. So this is at the condenser inlet, that is 0.703, multiplied by 10 atm is 7,600 mmHg, which thus gives us our vapor pressure of the hexane in this stream to be this value. Now we want to find the temperature over here. Now we can do that using the Antoine equation. We already have the vapor pressure of hexane in the stream that enters the condenser, and we can get the parameters from table B.4 for A, B and C and calculate for TO. So after we substitute them in, we get TO to be 187 degrees Celsius. Now let's look at the outlet stream from the condenser. Same thing, we use this equation, but because there's no specification of the relative saturation, so the mole fraction of hexane is 0.05. Okay, so YH multiplied by the pressure in that stream, which is 10 atm as well, 7,600 mmHg, which gives us 380 mmHg, and this equals to your hexane vapor pressure in this stream over here. Having this vapor pressure in this stream, we can calculate for the temperature of the gas stream leaving the condenser, T1. Same, using the Antoine equation, substitute your pH over here, and substitute your A, B, C parameters into the Antoine equation and calculate for T1. In this case, for the outlet, the condenser outlet, we are calculating for T1. Okay, so we have found T1. Now for the volume ratio, the question wants us to find the volume ratio of the outlet to the inlet. So taking PV equals to nRT, we can rearrange the formula and we can find that V is actually equals to nRT over P. So if we stack this together in the ratio form, V1 over VO is equal to N1 RT1 over P divided by NO RTO over P. So R and R is cancelled. P is the same, 10 atm, 10 atm. The only difference is the temperature. So we have N1 multiplied by the temperature in Kelvin. So you plus Kelvin over here, plus 273. Okay, divided by NO multiplied by the temperature in the inlet stream. This gives us, so we already know what is N1 and NO, and from here we have found T1 and TO, and that gives us a volume ratio of 0.22 meter cubic out per meter cubic in. Now, so when we determine which process is more cost effective, what we need to know is the cost of the cooling, which includes the installation cost of the condenser and the utilities and other operating parameters, versus the cost of compressing to 10 atm and cooling at 10 atm. So the energy used for condensing and cooling all of these needs to be taken into consideration of our cost calculation.